Okay, welcome to your first video in trig. Hope you're excited. So we actually have 3 parts here and 3 different days as far as basic concepts go. So this first week that we have is really an introduction to a lot of the things that you've already know from Algebra 1 or Geometry and Algebra 2. But we're harping on it a little bit more because all these concepts come up in trig. So this first little bit is not necessarily a review. Like, some of it is definitely review material, but some of the things you might not have seen explicitly in this way before. So the first thing that we're doing today is just talking about the quadrants, which I know that you've done a large amount of times, and I'm sure that you're familiar with them. But just as a reminder, we label our quadrants in the C shape, starting here at quadrant 1. And this was really actually an important concept in trig. It seems kind of weird that we're talking about it right now as far as where things are located. But when we end up talking about specific signs of trig values, trig functions, we need to know where that quadrant is, or it matters what quadrant we're in so that we know that, you know, the sign value is positive or the sign value is negative. So that actually comes up quite often. So the important part to note is that in quadrant 1 we have 2 positive values. Our x value is positive and our y value is positive. In quadrant 2 our x value is negative, our y value is positive. In quadrant 3 they're both negative, both x and y. And then in quadrant 4 our x value is positive and our y value is negative. So as we look through to decide where these quadrants are, where these points are in which quadrant, so our first quadrant or point that we have J is at a negative x value and a positive 7, so we're located over here in quadrant 2. And then our next one, point K, although this looks kind of weird, 3 root 2 and 7 root 3, we don't really need to know what those approximations are. The only important part to determine what quadrants it is in is looking at the sign values. So this here is positive, this 3 root 2. This y value here, 7 root 3, is also positive, so that means that we're sitting somewhere in quadrant 1. And again, we're not actually going to plot these points. I just need to know where it's located. And then M, this point M, is located at 0 on our x-axis and 1 on our y-axis. So that's actually locating not in a quadrant, it's actually located on the y-axis itself. So it's not really sitting in anything. It's not sitting in quadrant 1 or quadrant 2, it's on that axis. So that's like our first part of today, is just remembering that. Like remembering what the quadrants are, and an important part of what the sign values are for your x and y coordinates in those quadrants. The next part, which is most of the rest of what we're talking about today, is distance. So the first thing that we're going to do for our next example is to plot these points. So J here is at negative 3, 7. So that's up here, this is J. And D is at 2, 1. So here we go. So we are looking at the distance between those 2 points. So if we connect them, this line here, that's what we're looking to find. We're looking to figure out what that length is. Now, we can't count that length because it's at a diagonal. It's not like we're going from this point to this point, just moving horizontally or just moving vertically, and we can just count those units. It doesn't work quite that way. Instead, you probably remember it in geometry and in algebra 2, that we use the distance formula a lot. But before we actually get into that point, instead what we're going to look at is to create a triangle for this and see if we can figure out this problem a little bit more geometrically. So if I drop down this vertical distance here until it lines up with D, and I look at the horizontal distance here, so it lines up with that vertical line, what I'm creating here is a triangle. In fact, since these axes, our x and y axis, is perpendicular, we actually are creating a right triangle. So I'll redraw that off to the side so we can kind of see what we're looking at. So here's my right triangle, and I can just count these units now that I'm just moving horizontally and vertically. So I have 1, 2, 3, 4, 5, and in my vertical direction 6. So that goes here and there. So what we're looking for is this distance here. And if you remember, if you have a right triangle and we're looking for this is our hypotenuse, we can use the Pythagorean theorem. Already spelling Pythagorean wrong. It's a solid start. So we're going to use the Pythagorean theorem, which obviously we've already, or you have already dealt with, so you're probably really familiar with. Pythagorean theorem means when we have a right triangle, what we can do is use this a squared plus b squared equals c squared. These are my two legs of my triangle. They form my right angle, and then this is my hypotenuse. So in our triangle here, this value here would be our c. Now the converse is also true. So that means that if we have the Pythagorean theorem, we have some triangle, and the Pythagorean theorem actually works, like it satisfies. In fact, the two legs squared at the sum of the two legs squared actually does equal the hypotenuse squared, then we have a right triangle. So that's not the same. These are two different theorems, or this is the converse of that theorem. They're two different ideas though. One is saying if we have a right triangle, then this is true. This one's saying that if we have this being true, then we can classify it as a right triangle. It's the only case that it actually works in is a right triangle. So we're going to apply the Pythagorean theorem up here. Here are my two legs, 6 and 5. So I have 6 squared plus 5 squared equals c squared. So I'll just simplify that down. We have 36 and 25. So that's 50, 61. And to solve for c, we're going to take the square root, and I'm just going to leave it like that. We could find a decimal approximation, but I'm just going to leave it as the exact version. So there's my distance from J to D. Now the other way to do this problem is to look at the distance formula. Now what the distance formula actually is a generalized version of the Pythagorean theorem. So in this section, and you can kind of see where these things are coming from, or you can kind of see really similar features. We have some quantity squared adding to some other quantity squared. That's what we have up here, right? We have a quantity squared, We're taking the sum of those two things. So that's what we have. We also have this big square root, which remember we did do that big square root, or we took the square root of both sides down here at this final step. So this is the generalized version of getting to this section without having to go through this process. This distance between our x values that we have is the difference between our horizontal change. So we went from this point here, which was at our -3, and we moved to our new x value of 2. So that difference between those two values, which we're looking for in that horizontal change, is 5, which is where that was coming from. That was our one of the legs of our triangle. And then the other difference that we're looking for is the difference between our y values. And the difference between our y values, again, is really just our vertical change. It's our other leg of our triangle. So that is 7 and 1. 7 minus 1 is 6. That's why we're getting that 6 for one of our legs of our triangle. So really what this distance formula is the Pythagorean theorem. It just helps when we're dealing with things that are a little bit more messy. So like, for example, number 2, looking at the distance between these two things, this is something that's a little bit harder to plot. It's definitely something that's harder to actually draw a triangle for. So instead, we're just going to jump right into the distance formula between these two things. So we're looking for the distance between those two values. We're going to think about it in the same way where we're looking at just some horizontal change and some vertical change and imagining our triangle in our brains. But we can just apply it in that way. So the first thing that we're going to do is look at our two x values. So that's these two. And it doesn't matter which one you start with, as long as you're keeping some positive value when you square that. So I'm going to start with this one just because I know it's bigger. So I'll do 5 root 2 minus 3 root 2 in my first set. And then in my second set of parentheses here, again, I'm just going to start with this point, but you could start with that point even. We'll have minus root 3 minus 7 root 3. Now this is something that is maybe an extension of what you've looked at before. It's still the same concept. We're still using the distance formula, but this is a lot more messy. So I'm going to remind you how to actually deal with something that looks a little bit messy like that. So the first thing, if we treat this square root like an x, 5 root 2 and 3 root 2, it's the same quantity. We combine the coefficients that are in front of them. So ignoring the root 2, 5 minus 3 is 2, and then we'll tack on the root 2. And then the next one, again, same idea. We have the same quantity here, the same, they're similar terms because they're both dealing with that root 3. So we're really just going to look at our coefficients. So minus 1 and minus 7 is going to be minus 8, negative 8 root 3. And when we square them, when we square things that are two quantities here and then we have a square root, how we deal with that is we actually square both terms and then find the product of that. So we'll square the 2, which is 4, and we'll square the root 2. The square root of 2 squared just cancels out the square root, so we just get 2, and we'll multiply those together. And then to that, we'll add our next term, sorry, that's a plus. And again, we'll square both these values, so we'll square the 8, it's going to be 64, to negative 8. And then we'll square the 3 and we'll multiply them. So all in all, if I pull out my calculator, I'll have 8. And then this will end up being 192, I think. Let me just double check. Yep, so we'll get the square root of 200. Which that can actually be broken down. Our square root of 61 before, this is something that didn't really have anything that went into it that we could break down, so I left it just like that, the square root of 61. However, this square root of 200 does have a perfect square. Now you could use the cake method, you could use the factor tree, whatever you want to do for this. I like to think about 200 or this number and think about perfect squares that go into it. So I know that 100 is a perfect square that goes into 200, and 100 times 2 is where we're getting our 200, our product. So these two things multiply to get that number. And since I'm taking the square root, I can just take the square root of these two things individually and then take the product. So the square root of 100 is 10, and then the square root of 2 we can't simplify, so we'll just leave that as the square root of 2, and that is our simplified radical, our simplified distance between those two values. Okay, so this is maybe something that you've done before, like looking at those difference between even radicals when we're in squaring those terms. That should be more review. This should be more review. This should be a review. And I think you probably have done example 3 in some context, but the next two really might be a little bit different, something that you haven't quite done before in your other classes. So this is kind of that extension. So most of the things that we have, this basic idea, is something that is definitely review for things that you've already looked at, and hopefully you're a little bit comfortable in remembering where these things are coming from. But these next ones might be a little bit different. So our next example says that we have these points, and we're going to use the distance formula to prove that it's a right, this should say triangle. We're going to prove that it is a right triangle. So to prove that something's a right triangle, that means that we have to prove that it's a right angle, or we can show some other things are true about that. Specifically, what we're going to show in our case is that this is true, because that's what our converse is telling us, that we do have a right triangle if we can show that this is true. The Pythagorean theorem holds. So this means, does the Pythagorean theorem work? Does a squared plus b squared actually equal c squared? And if that's the case, great, we're golden. It's definitely a right triangle. Now, this triangle could look lots of different ways. So one of the ways it could look is triangle EFG. Now, nothing is telling me that F is actually the right angle. So it could look like that, or E could be the right angle, or G could be the right angle. So these are different pictures of what that could look like. Now, I don't really know which one's which. I don't know which triangle it is. We'll figure that out in a second. But for now, this is some picture that we're hoping to get out of our testing the Pythagorean theorem. And really what that means is that in any case, we need to find these distances between those 2 points. So we need to find the distance from F to E, whether it's here, whether it's here. Like it's either a leg or a hypotenuse. So we need to find that distance. We also need to find the distance from F to G. And then we also need to find the distance from E to G. So those are 3 distances that we need to find in order to prove that this is a right triangle. So we'll start with F to E. So we're looking at our distance formula here. So in our first set, we're looking at the difference between our x values. So E and F, that's here. So we have one of our x values is -9 and -1. So we'll have -9 minus -1. And then our second set here is our y values. So we'll have -2 minus -2. So our first set here, -9 minus -1, that turns into a plus. So really what we get is -8 squared. And then this actually cancels out. -2 minus -2 is -2 plus 2, so that term goes away. So really, that part's 0. And that means that since our y value is the same, really all we did if we actually plotted these points was we just went over horizontally. So we could have actually just counted this one. So if you can recognize that first, then that's great. So we'll get the square root of 64, which, not surprisingly, since if we can actually count the distance between those, we should get 8. So let's look at our next one, F to G. Okay, so we're using these 2 points now. First set, I'll put the difference between my x's. So you can start with either. I'm going to do this minus this. So -1 minus -9. And then in our second set, we're going to do the difference between our y values. So -2 minus 11. So again, -1 minus -9, that's going to simplify to 8. So we'll have 8 squared. And then our second one, -2 minus 11, is going to be -13 squared. So this will be 64. 13 squared is 169. And if I add those up, I should get 233. Square root of 233. And then our last one, last distance that we have is E to G. Okay, so E to G, I'm looking at the difference between my x values. And again, what you'll notice in this first set, -9 minus -9, those will cancel out, which means, again, for this one, and we'll see this in a second, our next set is going to be -2 minus 11. Since our x coordinates are staying the same, what we're really doing is we're just moving this point up vertically however many units. So this is another one that we could just count because our first set here, -9 minus 9, is just going to be 0. And our second set is going to be -13 squared. So this is one that we could have just counted. We should get 1 square root of 169, which, not surprisingly, is 13. Because that's the difference between our x, or y coordinate, y1, and then y2. Okay, so here's our values. Again, we don't really know what this triangle looks like, but now that we actually have these distances, we can actually form a better picture of what we have. So this 8 value, if we compare all the 3, 8 is the smallest that we have, 13 is the next largest, and then the square root of 233 is definitely bigger than the other 2. So right here, this is my hypotenuse, because it's bigger than my other 2 values. So these 2 are my legs. So what I want to do when I'm looking at the Pythagorean theorem, deciding if it works, this tells us what values we're going to plug in where. So these 2 are my legs, which are 8 and 13, because those are the the smallest and the second smallest. And the square root of 233 is my hypotenuse. So what I'm deciding here is, does 8 squared plus 13 squared really equal the square root of 233 squared? And if that's true, then we have a right triangle. So this should be 64, and 169. The square root of 233 squared will cancel out the square root, and we'll get 233. And I'm running out of room, but you will get 233 here equals 233. So since that's true, we'll say yes, triangle, what are we looking at, EFG is a right triangle, because the Pythagorean theorem is true. Okay, last idea here is looking at the distance between these two values or these 2 points in kind of a different way. So first thing I'm going to do is actually plot this point here, 1, 2, so we can get an idea of what's happening, what it looks like. So 1, 2 is this point here, U. My axes look a little wobbly. So we're finding this other point. We don't know this other point totally, but we know it has some x value and a y value of 6. And we're looking at the distance between that point, U, this one, and this other point, V, wherever it is 5. So I don't know what the x value for this new point is going to be. It could be anything. It could be 1, it could be 5, it could be negative 18. But I do know the y value is 6. So if the y value is constant, then that means that we're actually just sitting somewhere on this horizontal line. So somewhere V is at some point on that line. Now again, it could be anywhere, but then we do know if I plot it somewhere, so let's just pretend it's around here, then this distance that I'm going to make, this distance right here, this is the distance that's going to be 5. So we want that to be true. So somewhere we're going to like kind of swing that around and measure out where it would actually equal 5. Now, this is kind of a graphical geometric approach, a different type of problem than, but we're actually going to look at the more of an algebraic approach to it too, like looking at with the distance formula. So again, I'm just going to copy that down, x2 minus x1 and y2 minus y1 squared. And right now what I do know is that the distance is 5. So that's 5. And if I start to actually like put in what I know that this is some x value, this is some x value, so x minus 1 for my 2. And again, like you could do the other way for this one, since I don't know what x is, it's easier to just say x minus 1 versus 1 minus x. But it doesn't really matter. And then our second, or so difference between our y values, which are 6 and 2. Now if I start to simplify this, the first thing that I want to do, since the x is underneath this large square root, I can't just like simplify that and move it over. I'm just going to rewrite it though real quick. To do that, the 6 minus 2 is 4, so I'll have this. I can't like subtract 16 right now, because this 16 is underneath the square root. I can't simplify this x in here at all. So the first thing that I have to do, is, according to kind of my order of operations step, is to deal with this exponent. So to do that, to get rid of a square root, we square both sides. So we'll get 25 equals, and then these square root and the square go away, and we're left with what's underneath it, which is x minus 1 quantity squared plus 16. And now if I'm solving for x, I can subtract 16 from both sides, and I get 9 equals x minus 1 quantity squared. Now again, to solve for that x value, right now it's in something that's being squared. So the next step is to square root both sides. Now when you're taking the square root of both sides, this is super, super important. That's something you'll probably forget. Because it's really common too. It's one of the biggest errors that I see in trig, is that when we take the square root, we forget that we actually have to include a plus or minus. Now sometimes the situation that we're dealing with, like on the front, we didn't do the plus or minus when we took the square root solving for the Pythagorean theorem. And that was because we were dealing with a triangle, like we're dealing with this distance that, and we're solving for the distance, and the distance had to be positive. So sometimes we don't have to worry about that, like it won't actually affect anything. But this is a situation that we're solving for this x value, and this x value could be anywhere, right? Like with this picture, it could be over here, it could be over here. We don't know where that x value is, so we can't just pretend that it's always positive. So in order to, when we take the square root, we have to include that plus or minus because when we squared this, that thing was always positive, and we have to account for the fact that it could have been negative. So when we do that, we'll have plus or minus 3 on this side, and the square will go away. So this is our equation that we're solving, and when we add the 1 over to both sides, we get our two solutions of 1 plus 3, which is 4, and then 1 minus 3, which is negative 2. Now those are two x values that could work for that point. So we have v could be 4, 6, and v could be negative 2, 6. And remember, we knew that it had to be on that line. We knew that the y value couldn't change, so we're really looking at those two different x values. So this next part, you're actually going to finish that. Like that's going to be part of your next couple minute homework, is to try to think about this as a geometric application. We already drew a picture above in example 4, and see if you can put out into words why we can have two answers. Like why does it make sense looking at that picture that these two answers, or maybe you want to draw a new one and plot some new points, why does it make sense that both those would work? And what kind of explanation that you could you come up with to kind of generalize why there can be two answers to this problem, regardless of where we start, where u is, and regardless of where v is, or regardless of wherever that y value is. Okay,